Hello everyone. This lesson we're going to discuss unbalanced delta load. So we still have a 240 volt three-phase supply. We have a 30 ohm resistive load connected in delta. Under normal condition, we know the phase voltage equal to line voltage is 240 volts. The phase current is going to be phase voltage divided by the resistance. 240 divided by 30 ohm give us 8 amps. Delta connected load, the line current going to be √3 higher than the phase current. So √3 times 8 amps give us 13.9 amps. The total power at the normal condition, I use the formula 3 times E phase times I phase. 3 times 240 volt times 8 amps give me 5760 watts. That's under normal condition. One condition, unbalanced, we call it open line. We have a line B is open, so this circuit become a single phase circuit. In single phase circuit, we have two parallel branches. One branch is 30 ohm, another branch is 60 ohm. The line voltage is still 240 volts, but under single phase condition, we can calculate the total resistance in the circuit. 1/60 plus 1/30, 1 again, give us the total resistance is 20 ohm. With this 20 ohm and the 240 volt, we have 12 amps. Now, the single phasing or open line situation, the total power in the circuit is volts times amp, 240 volt times 12 amp, give us 2880 watts. Compare this power to the original power, we can see in single phase condition or open line condition, it only develops 50% of the original power. Next one, we're going to look at open load condition. Open load condition is considered open delta. So from our original drawing, we take one of the resistor out, which is in the phase C, we take that resistor out. They still have three-phase supply, but we only have two low in there. Phase voltage still equal to line voltage, 240 volts. For phase A and the phase C current, they equal to the volts divided by the resistance, give us 8 amp each. Line A is in series with phase A. It's also 8 amp at 0 degree. Line C is in series with phase C, so it's 8 amp at 120 degree. The line B is the one in the center, common to both phases. So the line B current is going to equal to the phase current subtract by using vector subtraction. If we subtract these two vectors, we got a line C current is 13.9 amps at negative 30 degree. The total power is going to be the power developer in phase A plus the power developer in phase C. So if we calculate the phase current, phase power in phase A and phase power in phase C, we got, add them up, we got 3840 watts. Compare this 3840 watts to the original 5760, we can see it's about 66.7% of the power developed in an open load condition compared to the original normal condition. Now I'm going to show you in the lab situation. This is a normal connected three-phase delta load. So I have my line voltage close to 240 volts. The phase voltage across each phase is also going to be 240 volts. My phase current is, when I measure here, is 7.3 amps. My line current, when I measure here, is about 12.8 amps. Now I'm going to simulate an open line condition. I close the power, remove one of the line, turn the power on. Now you can see when I measure this phase, it only measures 1117.6 volts. I can measure other phase. In here, I measure 235 volts. And if I measure here, it's also 117.8. So between phase A and the phase C, I only got half of the voltage across from phase B, because phase B is directly connect across line, two of the lines, and this A and the C is in series across the same line. Now I can measure the line current. My line current is 11.1 amps on both of the line. And the current goes through the phase, maybe one of them is only got 3.6. Another one got 7.5. So if we calculate the power, we can get, in an open line situation, only going to have 50% of the original power. Now let's look at the open delta, open low situation. Here's the open low. I remove the low C, so the voltage across low A and the voltage across low B still equal to 240 volts. It's my line voltage down here, 240 volts. But if I measure my line current here is 7.4 amps, equal to my phase current 7.4 amps down here. And on line C is also 7.2 amps, equal to my phase current 7.3 amps down here. But my line B current is 12.7 amps, is higher than another two lines. So measure again for three line current. Line C 7.3 equal to the phase current. Line B 12.8, the vector subtraction of two phase current. And the line A is 7.3 amps, equal to the phase current. So this lab we discussed open line and the open low situation in a three-phase delta low. If you have any question, you can connect us online or send us an email.